Friday, and welcome back to the second part of the equilibrium constant, calculating the K value. And this is module number 18. For module number 18, we're going to cover pages 21 to 24. And I just want to make you note that calculating this K value is going to be important because we're going to do it from now until the end of June. We're going to calculate K for an equilibrium. We're going to calculate Ka, which is going to be for a weak acid, because again, acids will dissociate just a little bit. And so we'll do that for weak acids. Then guess what? We'll calculate Kb for the equilibrium constant of bases. And then we put our acids and our bases together and we get water and we do our titrations. So once you learn how to calculate K and how to set it up, it's the same for all four calculations we're going to do from now on, okay? So this part right here is the second part where we just again look at the math and see, once we've calculated K, is K greater than 1? Is it 1? Or is it less than 1, okay? And so this can tell you the extent of the reaction. We can see, is the reaction still going in the forward direction? Is the reaction favoring the reverse direction? Or is this reaction at equilibrium, okay? Because we can tell that because the amount of reactant and the amount of product that we've got, once those are going where the rate of the forward is equal to the rate of the reverse, you're going to have concentrations that when they calculate out, mathematically you're going to get a value of 1 if that system is at equilibrium, okay? So here we go. If you calculate K, and again, you have to have the concentrations at equilibrium to be able to calculate the equilibrium concentration, so just keep that in mind, right? You've got to have what the concentrations are at equilibrium. It can't be an initial concentration or it can't be a final concentration. It's got to be what is it at equilibrium. Because you're calculating the concentration of the products over the concentration of the reactants, if the product concentration is greater than the reactants, then mathematically you're going to have a number that's greater than 1 because you're going to have a bigger number divided by a smaller number. So that should make sense. When that happens, there's a bit of terminology that we use, and here's the term. It says equilibrium favors the right, favors the products, is in the forward direction. So those are some of the terms that we'll use when we talk about equilibrium, so just be thinking about that, okay? If the K value is approximately equal to 1, then that means that there are approximately equal concentrations of these products and reactants at equilibrium. Well, what if at equilibrium our value is less than 1? If the value at equilibrium is less than 1, then this tells me that this equilibrium, when it's at equilibrium, you have a greater concentration of the reactants than you do of the products. Because again, mathematically, you're dividing a smaller number by a bigger number, and so you're going to get a ratio that's less than 1. How do we say, or what do we say about that or describe it? We simply say that this equilibrium favors the left or favors the reactants because the reactants are a greater concentration. Okay, do you get that? That's a little summary. Is K less than 1? Is K 1? Or is K greater than 1? That you're going to take with you. Okay, so I jot that down and you'll see where I do the summary page at the end, page 24. I've written it right at the very top, and then that can help you remember what the K value means with regards to the relative size of it. Okay, all right. Here we go. You're going to work through these questions, okay? Let's do the first one at the bottom of the page here because you can see based on that K value, what do you get? So this says, how would you arrange these equilibrium expressions in order of their tendency to form product? So that's saying to me, which one has a K value of greater than 1? Because to form product, you have to have more product than reactants. So mathematically, you're going to get a value bigger than 1. So which one, and can you put them in order? Yeah, look at the biggest K value. That's going to be 3, and then 2, and then 1. Okay, easy? Yeah? All right, don't get tricked by the second part of this question. It says, could you arrange these reactions from slowest to fastest? The answer is no, you can't do that because this is only telling you the amount of reactant and product you have at equilibrium and not the speed of the reaction. K is not related to the rate. It only means that when we've talked about rate, it's just that when you're looking at an equilibrium expression, something becomes equilibrium when the rate of the forward direction equals the rate of the reverse direction, nothing to do with the overall rate of making product or making reactant. Does that make sense? Okay. All right, let's move on. So you're going to calculate, and these pages again, setting up here so you've got the answer right underneath of the question so you can check your own answers, if you will. All right, second part that I want to talk about comes up right here. If you need to predict whether an expression is at equilibrium or not, you're going to calculate something called Q. Q is the reaction quotient. You're going to calculate it the same way that you would set it up for K, except you can't call it K because we don't know if it is at equilibrium. Does that make sense? So you've got to figure it out. If it's not at equilibrium, then you can't call it the equilibrium constant. Now, Q might end up being the K value, and then you can say, well, yeah, this system is at equilibrium because Q equals K. But if you don't know if it's at equilibrium, we're going to call it Q. Okay, so same thing here. Here you go. Here's your general equation. Yep, you're going to set it up the exact same way. Concentration of the products to the exponents, which were the coefficients. Divide that by the concentration of the reactants. And again, your coefficients become the exponents in that equation. And here's your answer. If the Q value is less than K, then the numerator of the expression must be relatively small compared to the products. The right side of the equation is smaller than their concentrations at equilibrium. The net reaction proceeds in the forward direction towards the right in order to get to equilibrium. Does that make sense? Because it's less than 1. So if it's less than 1, it's still going in the forward direction. If Q happens to be equal to K, well, then you can say that system is at equilibrium because we know that it is because it's the same value as K. And what if Q is greater than K? It just simply means that mathematically the numerator must be relatively large because the concentrations on the product on the right side of the equation are larger than the concentrations at equilibrium. The net reaction is going to proceed in the reverse direction, which is towards the left in order to achieve equilibrium. Okay, so it's really just the second mathematical part, but we can't call it K unless we know that it's at equilibrium, and this is what chemists would actually do. Is it at equilibrium yet or not? Well, do a little calculation using the concentrations and figure it out. Okay, so your answers are here, 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 and here. And that takes you all the way to page 24. And then this is our summary. This is our practice page right here. So once you've worked through all the little homework questions and you've checked all your answers and you get it, see if you can do this review. And can you see here that I've added that summary at the very top? Okay, this is what you need to remember. If K is greater than 1, you have a greater concentration of products. If K is equal to 1, you have equal concentrations. And if K is less than 1, you have concentrations of the reactants that are greater. Okay, that's what the equilibrium constant tells us. And then if you don't know if it's at K, then you've got to figure it out. And if the Q value, which is the reaction quotient, is less than K, then you know mathematically that means that the reaction is going in the forward direction. If Q is equal to K, then your system is at equilibrium. And if Q is greater than K, your system is going in the reverse direction to get to equilibrium. It hasn't reached that point yet. Okay, so you're going to be looking at the first 4 here. So go ahead and fill these in and then check your solutions. And I just wanted to mention this one here, where when you have a saturated solution, then if it's completely saturated, then what do? You show saturation by putting in the equilibrium. That means that the rate at which the lead iodide is dissolving is equal to the rate at which the ions are recrystallizing. The mass stays the same. The system is a dynamic system, yet you've reached a dynamic equilibrium because it looks the same. There's no macroscopic changes to it. And that is what it looks like when you've got a saturated solution. Okay, and the last part here is just applying Le Chatelier's principle. So give those questions a try, and that's it for module number 18. And we're actually almost done this whole unit. It starts off very slowly because, again, we want to learn about Le Chatelier and how to calculate K, and then we're going to bring it in and talk about acids and bases, and that is unit number 5. Okay, so good luck, and let me know if you have questions.